Hi, I'm Yang, and today I'm going to talk about min-cost flows, Markov decision processes, and L1 regression in nearly linear time for dense instances. To understand this, more generally, the problems we solve that capture everything I mentioned in the title is linear programs with two-sided constraints. This refers in the primal form to the following problem. We want to minimize C transpose X over vectors X satisfying a linear constraint. So this is A transpose X equals B for a matrix A that's M by N. This way, the vector X is M dimensional. The cost vector C is M dimensional, and this B vector is N dimensional. Additionally, every coordinate has a lower and an upper bound. So for all coordinates I between 1 and M, we have that xi is between Li and Ui. The dual form of this problem is instead to maximize over vectors y and rn, s and rm that satisfy ay plus s equals c, where here A is the same matrix as in the primal form, and C is the same as the cost vector in the primal form. The following quantity, B transpose Y plus sum over all I, min of Li Si and Ui Si. I'll get into some intuition on what this min term corresponds to. Algebraically, these are the following forms, just written more compactly. To understand how two-sided linear programs imply all the applications I mentioned in the talk title, here's how. So if A is a graph adjacency matrix, we actually get min cost flow or max flow. This is because C is the cost vector, X is the flow, is the adjacency matrix, and Li and Ui correspond to capacity lower bounds and capacity upper bounds on every edge. Additionally, if Li is 0 and Ui equals infinity, this corresponds to the standard form of linear programs, where the constraint is just X at least 0 and A transpose X equals B. On the dual side, this actually captures the problem of L1 regression in the following way. Imagine we take B equals 0, so the B transpose Y term is gone, and we take Li to be -1 and Ui to be 1. Then the min of Li Si, Ui, Si becomes negative of the absolute value of Si. S equals C minus Ay, so just get Ay minus C1 norm. So at a high level, this min, Li, Si, Ui, Si really is just like a shifted absolute value function. Additionally, it was shown by Sidford, Wang, Wu, and Ye that L1 regression implies Markov decision processes. For those who know, the parameters are M is the number of state action pairs, and N is the number of states, and that's what the correspondence is. In this way, L1 regression will give some runtime bound for Markov decision processes. Our results on graphs are the following. So here's the previous results on graphs. And in light of this, here is what we're able to show. What we give is a max flow or min cost flow algorithm that runs in time m plus n to the 1.5 times log squared of the maximum entry in the cost vector or the maximum capacity. So one way to interpret this result is that it was shown previously that you can get the same result, but only for bipartite matching problems. So our result extends this to flow problems. In some sense, bipartite matching corresponds to the standard form of LPs because there's not a two-sided constraint on the edges. There's only a one-sided constraint. The flow goes in some direction, not the other. Additionally, some co-authors and I have recently been able to extend ideas from this work to give a max flow algorithm that runs in time m to the 3/2 minus 1 over 328 log u. And this is the first algorithm that's faster than n to the 1.5 log u on sparse graphs. As for our results on linear programming, so for both these linear programs, both the primal form and the dual form, when A is an m by n matrix, we're able to give an algorithm to compute a high accuracy solution to this in mn plus n to the 2.5 time. This compares to previous results, which were able to achieve m to the omega runtimes, or nnza times root n plus n to the 2.5 runtimes. As you can see, these results are not nearly linear time for even dense matrices, while ours is for matrices that are dense, so almost all the entries are filled, and sufficiently tall, so m is at least n to the 1.5. For a linear program in standard form, a slightly weaker result was known. Mn plus n cubed was known. So, but our result works for linear programs that have two-sided constraints, not necessarily in standard form. Additionally, transferring from standard form to transferring from two-sided constraints to standard form might blow up both m and n enough that you can't actually just transfer to standard form and then use the mn plus n cubed result to achieve something like what we get. This point, I wanted to give some intuition for where these runtimes actually come from. I'm going to focus on the min cost flow case because graphs are easier to reason about in some way. To solve linear programs or the min cost flow problem, a powerful tool is the interior point method, which reduces these problems to solving a sequence of square root m linear systems in A transpose dA, where A is the constraint matrix. If A is a graph adjacency matrix, then A transpose dA is a Laplacian, and thus can be solved in O tilde of m time, so near linear time. Applying the factor one interior point methods and this runtime immediately gives an m to the 1.5 time min cost flow algorithm, and this was noted by Deitch and Spielman. So how do we actually get past this m to the 1.5? The first ingredient is that you can actually improve the root m iteration cost to root n. This is shown by Lee Sidford in 2014. Directly applying this shows that you can solve min cost flow in time m root n. So how do we change that m to another n? Well, notice that the graph Laplacian matrix has m, like the graph has m edges and the Laplacian has m entries. So solving it in less than m time is impossible in some sense. What we instead need to argue is that we don't need to solve the full Laplacian matrix. Instead, we can use an approximation or use a sparsifier of it, and that's actually sufficient. The sparsifier has n edges, so you can solve it in n time up to logs. Plugging this in is where you change that m to an n, and our runtime is m plus n to the 1.5. So the reason that there's a lot of difficulties with this intuition is that the graph still has m edges. So even though you're solving the sparsifier, you still have to relate it to the original graph. So what we have to do is actually use the solution that the sparsifier provides along with some heavy hitter data structures to detect when like edges in the original graph, like the true flow edges, change by a lot. And if we're able to detect any of these, each of these in O tilde 1 time, well, that's where the extra m plus n to the 1.5 comes from. We detect when every single edge, every of the m edges changes in O tilde 1 time, and we update those throughout the method. And that's kind of where the extra m comes from, or like why there's like difficult to actually get that last m to work out properly. In light of this intuition, here's our technical contributions. We formally analyze this method that uses sparsifiers, approximations, heavy hitters, a lot of other data structures with the two-sided Lee-Sidford barrier that gives the root n iterations. This is based on ideas from a lot of prior work. Robust two-sided interior point methods, like kind of what people have called it. One of the key data structures we need to implement each of these pieces in sublinear time is the data structure for maintaining Lewis weights of a matrix under a slowly changing diagonal scaling. Lewis weights are a fundamental importance measure in a matrix that I'm going to define. In fact, I'm going to really focus on understanding this data structure for the remainder of the talk, and I'll briefly discuss what the interior point method setup we use is. To build this Lewis weight data structure, we give a series of reductions. We start with this primitive heavy hitters that I mentioned. So the heavy hitter primitive is I want to maintain large entries in the matrix AX as the vector X changes, but the matrix A does not. We reduce maintaining leverage scores, which is a different measure of importance in a matrix, to heavy hitters. And finally, we reduce Lewis weights to maintaining leverage scores. So just to remind, heavy hitters, we use L2 heavy hitter sketch. This is the Johnson-Lindenstrauss lemma, or using it several times. On graphs, there's actually a more efficient way to do it via dynamic expander decompositions. But I'm not really going to focus on that piece. Let's just imagine we have such a heavy hitter sketch that maintains large entries of AX. At this point, I'm going to define Lewis weights. To define Lewis weights, we need to understand what leverage scores are. Leverage scores of a matrix A with rows A1 to AM, it's defined as AI transpose, A transpose A inverse AI. Intuitively, it's an L2 importance measure. So equivalently, you can say that the ith leverage score is the maximum value that the ith coordinate can contribute to the total L2 norm in a vector AX. So the sum of the leverage scores is n instead of m, which is some intuition for where the n's in our runtimes come from. And finally, you can actually approximate them very efficiently with like a couple linear system solves by using the Johnson-Lindenstrauss lemma. Lewis weights are a LP norm analog of leverage scores that are recursively defined. They're precisely defined as the unique vector W that satisfies W equals the leverage score of W to the 1/2 minus 1 over P times A. I want to emphasize again that this is a recursive definition, but it turns out that W is still computable and unique. Informally, these Lewis weights give a relationship between the LP norm of AX and some L2 ellipse that's induced by scaling A by W. Like leverage scores, they sum to n, and there's an algorithm to actually approximate them to 1 plus epsilon accuracy with the contractive map. So this works for any norm P in 0 to 4, and turns out in our algorithm, we actually take P close to 1. To understand why we take P close to 1, recall that the problem we're solving is ℓ1 regression. So a standard interior point method solves diagonal scalings of A. In other words, A transpose D squared A for diagonal matrices D. What the Lee-Sidford algorithm says is that instead of using these naive diagonal scalings, we're going to additionally reweight it with the L1 Lewis weights to more capture the structure of AX1 norm. We end up taking P close to 1 because the problem is ℓ1 regression. And formally, we actually have to take P slightly less than 1 to get the analysis to work out properly. Given this, and the fact that we want to maintain all these updates inside our algorithm sublinear time or implicitly, this leads to the following data structure problem. Let's maintain the LP Lewis weights of matrices G times A while the diagonal scaling G changes slowly. So like, let's say 1 entry at a time. What we're able to show about this problem is that for a matrix A that's m by n, some P in 1/2 to 2, so let's say P approximately 1, in a positive diagonal scaling G, which is initially the identity, we support the operations, initialize the data structure given these matrices P and G. We can scale any entry of G. So we just take some entry GI and just reset it to any positive value. And finally, we can query what are the coordinates in the Lewis weights that have changed by more than a 1 plus epsilon factor because of these scale operations that we're doing. So these scale operations work in n time for general matrices and O tilde 1 time for graphs. Query works with the similar runtime to scale up to epsilon to the minus O of 1 factors. We end up taking epsilon to be polylogarithmic, inverse polylogarithmic. So these are all just O tilde 1 factors. Previous works were able to achieve such a data structure for the P equals 2 case. This corresponds to leverage scores, and we actually use this result to build our Lewis weight data structure. There's 2 key pieces that we use to build our data structure. The first is that there's a contractive map to compute Lewis weights approximately by reducing it to a sequence of leverage score estimations. Precisely, the contractive map takes our current weight vector W and changes it to something else, W to the 1 minus P over 2 times the power of the induced leverage score. And you can show that each application will actually decrease the approximation error to being the true Lewis weights by a 3/4 factor. We recursively plug this into a data structure for leverage score maintenance of matrices with changing diagonals that was shown previously to get our data structure. Pictorially, we have the following. There's a multi-layer data structure. Every single layer of the data structure, of which there's ℓ1 layers, is a leverage score data structure that maintains epsilon over 100 approximate leverage scores under changing diagonals. In every single layer, we implement a contractive map. So one layer asks for what is the result of the contractive map, and it asks that from the previous layer. And as mentioned, every single layer decreases the accuracy of the Lewis weights by a factor of 3/4. So the top level, it's epsilon. At the next level, it's 3/4 times epsilon. So after L levels, think L is a constant. You've decreased the error to 3/4 over 3/4 of the L times epsilon. So let's say that we were able to decrease the approximation error by a factor of 10. Well, then what you can do actually is plug it back into the first layer, and you can show that you only lose a constant factor in approximation when you do that. So having this multi-layer structure allows us to maintain Lewis weights up to an epsilon approximation, which was our goal. Understand why this runtime is good enough. We will use a guarantee from the leverage score data structure, which basically follows from the fact that it's actually very efficient. So each level in the leverage score data structure will pass amortized epsilon to the minus ℓ1 updates to the next level per query. There's ℓ1 levels, so the total number of passes downwards is epsilon to the minus ℓ1, raised again to the power of ℓ1, which is up to log factors, epsilon to the minus ℓ1 again. That's at a high level how the analysis works. At this point, I'm gonna switch into giving a high level overview of what the two-sided interior point setup is. So for this linear program, with two-sided constraints, so this is xi least li and most ui, what an interior point method does is it sets up a logarithmic barrier, log x minus li, log ui minus x, to constrain x to be between li and ui. The central path of the interior point method regularizes the linear program with these barriers, with an additional weight by the Lewis weights. This is where the Lee-Sidford part of the analysis comes in. So we take C transpose X and we add mu times the Lewis weight times these barrier functions. And we would have maintained minimizers of this approximately. By the KKT conditions, you can show that there's dual variables y and s, such that ay plus s is c, and we actually want to maintain that s plus the mu w phi prime of x is 0 in all coordinates. For this KKT condition, we only maintain it approximately, like most situations in our algorithm. By approximately maintaining this KKT condition, what I mean is we set up a softmax potential. So this is sum of x of lambda times kind of what like the s plus mu w phi prime x that we're actually maintaining. So this, we want it to be 0, but it's not actually 0. And then we normalize it by some normalizing factor. The invariant we maintain is that psi is at most a polynomial in M, for lambda is logarithmic over epsilon. So if we're able to maintain this invariant, what this shows is that every single coordinate, the error is epsilon on average. And that's actually enough to push the method through. Also, seeing this kind of explains where a lot of the difficulties in the analysis come from. Basically, in the analysis, we have approximations of S, mu, X and the Lewis weights W at all times, and kind of tracking how these errors propagate and approximations propagate is where a lot of the difficulty in the analysis comes from. To conclude, in our work, we gave improved algorithms for two-sided linear programs and the max flow problem. To achieve this, we gave an analysis of interior point method with a two-sided Lee-Sidford barrier and several approximations throughout that I just mentioned. And we gave data structures for implementing this interior point method. A highlight of these data structures is we give a data structure for maintaining Lewis weights for a matrix with slowly changing diagonal entries. We achieve this by reducing Lewis weights to maintaining leverage scores, and by reducing leverage scores to maintaining a heavy hitter on a matrix AX where X is changing. By combining these ideas, we're able to achieve an M plus n to the 1.5 time algorithm for min-cost flows, an Mn plus n to the 2.5 time algorithm for two-sided linear programs, and ℓ1 regression or Markov decision processes. And that's my talk. Thanks.